Hi, welcome to the first lecture of ME 201 Fluid Mechanics course. And this course is offered for third semester students of the School of Mechanical Sciences, IIT Goa. So the complete syllabus of this course can be found in the course website given in the video description. Okay, so today we'll start with chapter 1, which we call in which we discuss some introductory concepts of fluid mechanics. Okay, so we will start with the definition of what a fluid is. Okay, so what do we mean by a fluid? Okay, so there are three states of matter that are commonly found on earth. Okay, you know them from your school physics. So the three states of matter. Okay, we are concerned about commonly found states of matter on earth. There are three of them. You know that solid, a liquid, and gas. Okay, so you also know that existence of matter in these states are dictated by intermolecular attractive forces within these substances. Okay, and you know that solid has the strongest intermolecular attractive forces, and gaseous phase has the weakest forces, and liquid lies in between. Okay, so this classification is based on intermolecular attractive forces or intermolecular forces, let's say. Okay, but from mechanics point of view, we do not bother about these intermolecular forces. In mechanics, as you already know, we are concerned about how bodies respond to forces. Okay, when we apply forces, how do the body under consideration will respond? Okay, that is always our focus in mechanics. Okay, so based on this, there are only two states of matter. One is solid and another is fluid, that combines both liquids and gases. Okay, although liquid and gases are completely different in terms of their molecular construction units, the governing equation the equations that govern the behavior of these are the same. Okay, so liquids and gases are called as fluid together, and equations governing their mechanics take the same form. Okay, so that is why they are grouped together in this category called fluid. Okay, so in order to show the difference between a solid and fluid, let us consider a following simple experiment. Okay, so consider a simple experiment. Okay, so we take a solid. Okay, and let us say this is our solid. Let us say this is applied, so this is subjected to a shear force tau. Okay, let us apply a constant shear force at the top surface, and the bottom is fixed. Okay, so what would happen? upon application of this shear load, the solid deforms, okay, and attains the equilibrium because the applied shear force is constant. Okay, so this is theta, this is theta. Okay, so upon loading, you know that solid deforms and the tau is kept constant, so it attains equilibrium. Okay, so when we say equilibrium in this case, okay, so under equilibrium theta is constant. Okay, so the solid deforms to a particular amount of theta for a given loading, and when the body obtains this, we say that it is in equilibrium. Okay, and when we remove the load, what would happen? Okay, so assuming that the body is within the elastic limit, the body comes back to its original position. Okay, upon load removal, the body comes back to its original position, which means that the quantity that describes deformation goes to zero if the body is deforming within the elastic limit. Okay, so this is what would happen if we consider a solid. Okay, so now let's move on to fluid. Okay, we have not defined a fluid from mechanics point of view, which we are going to do it after this experiment. Okay, so a similar experiment on fluid would be that we consider two plates. Okay, very very long infinite plates where we keep the bottom one fixed and we apply shear force to the fluid. So the fluid is filled between the gap between the plates, so we apply a constant shear force at the top by moving this plate at a particular velocity. Okay, so that will induce shear on the fluid which is filled in between the plates. Okay, in order to see what would happen, let us consider particles of fluid that lie initially along this vertical line. Okay, so this is at t equals 0. Okay, we consider a couple of particles that lie on any particular vertical line. Okay, but as time passes, what would happen is that this will start deforming. Okay, they will still be on a straight line. Okay, so this will be t equals t1, and then when time increases, the bottom one will not move because the bottom plate is fixed. Okay, but so this is what would happen at t equals t2. It should be a straight line. I didn't draw it correctly here. It should be a single straight line. Okay, so what happens here when we fill a fluid between two plates and apply a constant shear? What happens is that the fluid starts deforming continuously. The fluid deform continuously. Okay, so the continuous deformation is the key word that defines fluid. Okay, we'll come back to this point. Okay, under equilibrium, what would happen? Any guess? Any guess? Okay, in solid, under equilibrium, the deformation becomes constant or strain becomes constant, but under equilibrium here, the rate at which the deformation happens becomes a constant. Okay, It is not, the deformation itself is a constant for a fluid, but the rate at which the deformation happens becomes a constant. Okay, and upon removing the load, the fluid does not come back to its original position as in solid. What would happen is that upon load removal, the rate at which deformation happens goes to zero, or in other words, fluid will come to rest. Okay, so this is the fundamental difference between solid and a fluid from a mechanics point of view. We take a solid subjected to a constant shear force. Under equilibrium, the body will attain an equilibrium, and under equilibrium, the deformation becomes a constant. Okay, you remove the load, and if the body is deformed within the elastic limit, the body comes back to its original position, making the deformation zero everywhere. Okay, but when you take a fluid and subject it to constant shear force, it starts continuously deforming. Okay, so under equilibrium, the rate at which the deformation happens becomes a constant. So in this case, what we have here mentioned is the shear rate, which we will talk about it by the end of the class. And upon load removal, the fluid will not come back to its original position, but it will stop deforming, or the fluid will come to rest, which means that the rate of deformation is zero. Okay, now to proceed further, if we want to discuss it a little bit further, solid from mechanics point of view is quantified by this relation. Stress is proportional to strain for a solid. Okay, you know this is Hooke's law for a solid, for a linearly elastic solid. But for a fluid, stress is not proportional to strain. Stress is proportional to rate of strain. Okay, tau is proportional to theta here. Tau is proportional to d theta by dt here. Alright, so that is because if tau goes to 0, the deformation goes to 0 in solid, but in fluid, if tau goes to 0, the rate of deformation goes to 0. Okay, so this is the difference between a solid and fluid from mechanics point of view. Okay, so if somebody asks you what is the difference between solid and fluid, you should be talking about this from now onwards. Okay, fine. So based on this, let us define what a fluid is. Okay, so definition of fluid. Okay, so fluid is a substance that deforms continuously under the action of shear forces. Okay, however small the shear may be. Okay, so the key point here is, again, I am stressing it, is the continuous deformation. A fluid deforms continuously under the action of shear forces, however small the shear may be. Even if the shear is very, very small, the deformation will be continuous. Okay, and this act of continuous deformation, this act of continuous deformation is called the flow, the fluid flow. Okay, so when you mention a fluid is flowing, you are actually referring to this continuous deformation. Okay, so in fluid mechanics, what are we going to learn? Okay, so in fluid mechanics, we are going to study fluids at rest, okay, and in motion, and importantly, interaction of fluid with the solid bodies. Okay, so this is the focus of this course called fluid mechanics. Okay, we are going to study fluids at rest as well as in motion, the interaction of fluids as well as solid bodies. Okay, this gives rise to many very interesting phenomena which we are going to discuss in this course. Okay, so before we discuss about the importance of fluid mechanics, I mean, why do we bother about fluid mechanics, let us discuss what do we call as Newtonian fluid. Okay, so Newtonian fluid is analogous to elastic solids, which you already know, or linearly elastic solid if you want to be more specific. Linear elastic solids. Okay, so before we come to Newtonian fluid, let us talk a little bit more about the rate of strain. So in the previous discussion, we wrote tau is proportional to the rate of strain. Let us talk a little bit more about the rate of strain. So we are going to write rate of strain in terms of velocity of the flow. Okay, so in order to do so, consider a particle P. Okay, let us say a particle P, and then we consider two fluid elements adjacent to this. Okay, so these two are fluid elements located at a distance delta y from each other. Okay, so this is at t0. So the bottom one moves with velocity u, and this one, which is slightly away from point B, this will move with u plus del u, a slightly different velocity than this layer. Okay, so this is at t0. What would happen at t plus delta t? Okay, so this particle, the one above, would have moved a distance of u plus delta u times delta t. Okay, the velocity times multiplied by the time will give you the displacement. Okay, and this would have moved to a distance of u times delta t. Okay, okay, so this is at t plus delta t. Okay, so let us say this angle is delta theta. Okay, so how can we write delta theta here? So tan delta theta. Okay, when dt is very small, delta theta will also be very small, so which will be equal to delta theta. Okay, so that will be, so this distance, this will be equal to this distance, okay, which is delta U times delta T, okay, divided by delta Y here. Okay, delta Y is this vertical distance, okay, opposite side by the adjacent side. Okay, so when delta T is very small, okay, so limit delta T tends to 0, we write delta theta as d theta by dt, which we can write from here as du by dy. Okay, so this is the relation that we wanted to get, right? So we related an unknown quantity called rate of strain to velocity, which would be a known, or it's not known, which is a measurable quantity in a fluid flow. Okay, so the rate of strain is equal to the gradient of streamwise velocity in the transverse direction. Okay, so I should have drawn the coordinate system in the beginning, but let's say this is x and y. X component of velocity is u. Now we see that du by dy is the gradient of streamwise velocity, the velocity along x in the transverse direction, y. Okay, so we can write the stress strain relation as tau is proportional to d theta by dt. Using the above expression, we write tau is proportional to du by dy, and the constant of proportionality, we write it as mu. This mu is coefficient of dynamic viscosity. Okay, so we will discuss about coefficient of viscosity in the next chapter. Okay, so fluids that obey the linear relation between stress and strain rate are called Newtonian fluids. Okay, so fluids that obey linear relation between shear stress and rate of shear strain are called Newtonian fluids or Newtonian fluids. Okay, so they are analogous to linear elastic solid, in which stress is proportional to strain, which is given by Hooke's law. Okay, in the entire course in this ME201 fluid mechanics, we will be concerned only about Newtonian fluid, because Newtonian fluids are very important, because most of the fluids occurring in engineering, like air, water, or oil, etc., which are important for majority of the mechanical engineering applications, are Newtonian. Okay, so in the entire course we are going to be talking only about Newtonian fluid. Okay, now let us ask ourselves this question: why fluid mechanics? Okay, so why should we care about fluid mechanics? Okay, what are the uses of studying fluid mechanics? Okay, in order to answer this question, I am going to show you a short presentation now.